Faisal is the National Measurements Institute of the Netherlands. We are located in Delft. It's quite a small country, it's like Pakistan, and all the cities are actually also much more smaller. The nice thing about Delft, which you can see here, is that we are located next to Delft University of Technology. So we have a very big campus here, and we have also very strong collaboration with them. That makes it all more easier for us to collaborate with the university in Delft and exchange and collaborate on various research projects. Now, BSL, being the National Measurements Institute, is tasked by the government of the Netherlands to maintain and develop the national primary standards. And what does that basically mean is that we need to support the industry by providing the necessary measurement infrastructure for the development of wide range of technologies which are needed by the industry within the Netherlands. And that means that our role is primarily limited to traceability. So we're not a conventional calibration lab, as one necessarily can think of, but our primary role there is to provide traceability. And in doing that, we need to support the development of primary standards which are needed for such cases. Now, a bit of facts. BSL is basically a much smaller National Measurements Institute than many think. So it's about 110 people, of which about 60 to 70 are basically the scientific staff. We have about 3,500 square meters of lab space, used for a wide range of applications. One can think of electrical measurements, mass measurements, dimensional measurements, optics, chemistry, flow, and so forth. Temperature, we have a very nice temperature group as well. So what does the National Measurement Institute do? If you look at the need for accurate measurement, it has been there for many centuries. Think about time, think about weights, think about dimensions. All of these units have been quite important for many centuries. And the need for accurate measurement is only growing. So the need for accurate measurement is only growing by the day. If you look now in the present day society, I think, can you hear me?
Yes. It might be better if you...
Okay, of course.
Easier for you as well.
Yeah. Working. That makes it easier. So, in the present day society, if you now look at the number of applications that require accurate measurements, it has increased tremendously. And what we now foresee in the near future, that with the applications like IoT, with devices, all of them are actually interlinked. And not only are the measurements per se used individually, we combine data to make better decisions. And that's what it's all about. With accurate measurements, we need to be able to make more accurate decisions. So, high frequency metrology is the group that I lead at VSL. We serve a number of domains. Think about telecommunication networks, think about space applications, satellite communications, space imaging, military applications, wide range of military applications, semiconductor industry, healthcare, and of course autonomous vehicles, for example. One thing that all of these applications have in common is that they need accurate measurements to make more and better decisions for those applications. Now, in high frequency metrology, the most accurate instrument in up to even terahertz at this point of time is still the network analyzer, vector network analyzer. Basically, this is the workhorse instrument that you need if you need to do anything on RF. So the first instrument you buy is a VNA. And nowadays, the early generation of VNAs developed in the 70s was simply a resistance meter, for example, single pole resistance meter. But over the decades, it has developed into pretty sophisticated scientific instrument, able to measure a wide range of parameters. And not only the measurement range has been increased, but also the dynamic range, meaning frequency. Whereas the early instruments were able to measure only up to a few megahertz, nowadays the present generation of VNAs can easily go beyond 1 terahertz in frequency range, right? Using different frequency extenders and so forth. So that's also the reason why our group at BSL basically focuses our R&D resources primarily on research and development on VNA metrology. We do a lot of VNA measurements for a diverse range of applications. Think about measurement services where we need to characterize connectorized devices. Think about devices on wafer, so when you actually need to characterize devices very close to the integrated circuit itself. And all of these measurements, because VNA, the big advantage of a VNA is it's very fast instrument. Within a few seconds, you collect thousands and thousands of measurement values for a broadband frequency range. Now, collecting all that data is one thing, but then processing it, calibrating it, calculating the accuracy and certainty as well requires some sophisticated software as well. So a lot of effort of our group has gone into development of such a measurement software. And then, of course, extending that measurement capability that we primarily developed for the connectorized and wafer on planar devices, we also focus on certain applications that need more accurate measurements. Think about extreme impedance devices, nanoscale devices. Physics groups at Delft University have been developing very small on-wafer devices. Think about carbon nanotube, for example. Now, how to characterize those? And of course, now extending the frequency measurement capability of a VNA to cryogenic conditions. Think about quantum applications, quantum computing, where you need our sensing ability. And now with the present generation of quantum computers extending the number of bits to a much higher number than what currently is being done, well, basically they need now more accurate S-parameter measurements as well. So, keeping time in mind. So let me give you an overview of what it takes, and because I know that the audience today has a very different background than mine, so I will keep the high frequency stuff a bit generalistic and try to explain why we actually spend so much effort into doing these measurements so rapidly. And the first measurement capability that our group developed was that of connectorized devices, because these are the type of devices that are basically needed to calibrate your equipment in the first place. So when you buy a VNA, you buy a calibration kit for that VNA. And that calibration kit needs to be calibrated by an NMI like us. Now, how to develop a measurement facility for calibration of such devices? And here you can see an overview of such calibration standards. And some of these are pretty old, but the nice thing about having a lot of measurement history for calibration devices gives us also more ability to analyze the stability of such a device. Now, going from a simple measurement, because measurement itself without an accuracy estimation doesn't mean much for us. A measurement gets a value, and with that value you need to say something about the accuracy of that measurement. And that's what we call an uncertainty. And a measurement, as you can see here, with an uncertainty contribution, that's something that we're looking for. At the end of the day, we need to develop a measurement capability which allows us to estimate an uncertainty for that particular measurement. Now, here you can see an overview of a VNA measurement system which is designed for characterization of connectorized devices at VSL. And another thing that's important here to notice is that VNA itself is not alone. A system comprises of many things. You need a VNA, of course, but you need very accurate cables, you need very accurate test port adapters, and of course you need a very accurate and stable table on which you can actually put such a system. And one thing that you don't notice is the environment. the environment in which this system is actually positioned. Because the temperature, we monitor the temperature within a half a degree, so it's 23 degrees plus minus a half a degree, and the humidity is monitored within a few percent. And that's something that needs to be done if you want to produce consistent measurements over a long period of time. So many years, you want to be consistent over many years, this is what it takes. So how to do it, for example, for VNA? A vector network analyzer basically measures two important parameters, an impedance and transmission. Now for impedance, we need coaxial transmission lines, because those transmission lines actually are a primary reference standard for impedance, meaning we can measure the dimensions of such a transmission line, and based on those mechanical dimensions which are traceable, we can actually use those mechanical measurements to compute the electrical impedance at high frequencies of such transmission lines. And that information is then used for calibration of a VNA. And this is what is needed for a primary calibration. So if you start a VNA and you don't have an NMI around the world to give you calibrated calculator, this is what you need to do to develop your own traceability. So here you can see a setup which is used to measure the mechanical dimensions of a transmission line designed by one of my students in, I think, 2015. And along the length of the line, we measure the diameters. Then we have a model in CST which we developed to use those mechanical dimensions and then compute the electrical impedance. And here you can see a very nice impedance comparison with the measurement. You don't see the bottom line, but that's acknowledgement. Now, the second parameter for VNA is like, for example, the attenuation. For that, we need to have a primary setup that measures the attenuations much more accurately than VNA. So here you see a dedicated setup which we designed for attenuation measurements. And this system can calibrate attenuations up to 80 dB with 10 millidB accuracy. So that's pretty good. But that's what you need to calibrate, for example, automated attenuators, which is subsequently used to characterize the linearity of your VNA. Right? So these two setups are needed, but apart from that, if you want to estimate an accuracy of your measurement, you need to look at every element which is involved in that system. For example, RF cables. Regardless of whatever you build in high frequency measurements, you will be using cables. Accurate cables, and we buy some of the best cables that you can buy, but even those cables and connectors are actually imperfect. For example, these metrology grade connectors, as you can see, they still have some mechanical tolerances. So the those manufacturers that manufacture these connectors, they still have some tolerances due to which you will get some errors. So what we do is we actually characterize even these connectors. We put them under microscopes, we measure all the dimensions, which is immensely time-consuming task. Then we put them in CST, we build EM models of them, we do a lot of simulations, time-consuming simulations, and then we predict the effect of such an imperfect connector. And if you have about 30 to 50 connectors, which we do, it can be a very time-consuming task. So, and here you can something that we do for like monitoring the pin gap effect. Now, why do we do that? Here you can see in reflection measurement of a mechanical precision transmission line. In one of the measurements, and this is the result coming forward from the same transmission line. The only thing that we did is that we positioned the center conductor in one of them using such offset discs, which basically are there to de-embed the pin gap effect that we get from such imperfect connectors. And if you don't use them, you can see the difference between the two measurements is actually much bigger than the accuracy that we claim. So it makes sense to actually even align these transmission lines with about 10 to 20 micron offsets. Even those dimensions matter and are actually critical. So cables, which I was talking about, we can buy one of the best cables in the world, but still they are imperfect. They still introduce errors. And it's all about measurement and accuracy. So every element that's involved in the system, we need to individually characterize its influence. So how do we characterize the influence of the cables? We build this very nice robot here, which is basically a motorized cancellation stage. We mount the cable and we move the cable in a very specific way, the way that we use it also in the measurements. Then, using the data, we estimated the most accurate position
positions at which we need to operate the cable to get even better performance. And we're talking about very, very small numbers here. So this graph shows you some of the data. I think this is the influence of the cable at 50 gigahertz. And all of these accuracies, so every element is individually characterized, the instrument itself, the cables, the connectors, the calibration standards, and then combining all the data, we actually estimate the accuracy of a DUT, which you can see here. And that calculation process, for that we have a dedicated software. Now, after developing the capability in the connectorized domain, the next challenge for us was to extend this measurement capability in the planar domain on wafer measurements. And that's actually where the things start becoming even more complex. And the reason for that is that if you now look at the trend of semiconductor industry, these transistors are becoming smaller and smaller. Now, in this prediction by Intel, basically what they claim is that in 2030 they actually are planning to embed 1 trillion transistors on a package. That means an extremely small transistors. But not only that, the more complex thing that is now happening is they are stacking these integrated circuits. So the 3D packages, that makes it even more complex to measure such a device. They're not only becoming smaller, they're actually stacking these things. And furthermore, which is happening as well is they're actually going to use more and more exotic materials, meaning these materials are offering much different impedances than the conventional devices are at this point of time. So the instrument itself, which we have, the VNA, is designed to measure these 50 ohm devices very accurately. But it is very inaccurate at other impedance levels. And apart from that, the frequency are continuously increasing. Whereas a few years ago, we were actually very well equipped to deal with measurements up to about 109 gigahertz. Nowadays, these measurement capabilities extending beyond 1 terahertz, which makes it also a very complex situation. So, to deal with all these challenges, smaller sizes, exotic materials, higher frequencies, we saw the need of developing our own probing system. And this is the first actually a system that you need to even think about on wafer measurement. Because how to even probe a device which is about 30 nanometers. So you can't do it with your plain hands. And for that you need such a robotic arms, which we actually call positioners. And on these positioners we have the probes, which then contact the device and the test. Now, we are the only NMI in the world who have developed their own probing station. You can buy these commercially, which are available, but the problem with commercial setups is they are not designed specifically to serve metrology institutes like us. They're designed to serve a very broad industry. And for that industry, at this point of time, accuracy is not the highest priority, the speed is. And for us, of course, accuracy comes at number one. So we decided to design this system ourselves, and this is a system prototype, the first prototype coming forward from a collaboration between DSL and Delft University of Technology. So one of my students was involved in designing this first prototype, and we used these pico motors to design the position. And these are very nice motors because they were able to actually provide us a translation step of about 20 to 30 nanometer. And that's substantially better than what you commercially can buy at this point of time. What we also did with respect to the was to by increase, we added another microscope. Conventional systems only have a top view microscope in the vision system. We added a second camera to allow us better visualization of the probe-substrate interaction. And here you can see the side view of a probe, and you can see here that how much you learn much more by having this side view instead of only the top view, which you have in the conventional systems. I will later on explain why we do that. Now, in on-wafer measurements, the situation is a bit more complex than the connectorized domain, which is very closed domain. You have a very well-defined reference plane, meaning your device under test is insensitive to the system, and the system is insensitive to the device under test. The problem in the planar domain is this doesn't necessarily hold anymore. The device affects the system, and in the same way, the system affects the device itself as well. And the challenge for us is to actually ensure that that sensitivity is negligible. And the main component affecting this are the probes. And when you actually move from this connectorized domain to a planar domain. Now these probes, which you can buy commercially, come in many different types and sizes. That makes it also more complex. If you want to do accurate on-wafer measurements, you need to first understand the influence of these probes in a better way. And doing that, it means is that we need to develop equivalent models and then study those models in these 3D EM simulation tools. Now the problem here is that most of the probes that we commercially can buy, you don't get any information on them. It's more the IP of the manufacturers, and they don't simply provide that information. So what we did is we investigated these probes under microscopes, tried to assess the dimensions of these probes, and using this information we build equivalent models in simulation tools such as the CST Micro Studio. And then using these simulation tools, we investigated the influence of these probes and the sensitivity of these probes to a wide range of applications. Now here you can see, for example, when the termination impedance of the probe is changed, they produce a different crosstalk. Now, unfortunately, side effect of these probes is that they radiate energy as well. So besides having the modes going through the substrate alone, you also have a radiation, meaning these crosstalk terms are sensitive to the distance and the impedance, which makes it even more complex to deem that from the results. Now, here we investigated the sensitivity to the impedance, but also the distance. When you vary the distance between the probe, the magnitude of the crosstalk term also changes. Now, these are the things that we need to do to understand each and every element of the system. And once we understand the influence and we can quantify that influence, that's where we actually then can start thinking about calculation of uncertainties. Now, the next step, so the first step was to design the hardware, the probing system. Once we had that, we needed to start thinking about this probe and substrate interaction. Presently, the big problem in on-wafer measurements is that they rely on manual probing techniques. So basically what that says is the experience of the user plays a very, very important role in the accuracy of the measurement. If you're very experienced and you know exactly how to probe a device, you will produce a much better accuracy, repeatability than someone who has less experience. And that's something that you don't want in a metrology institute, where you need to guarantee a consistent and user-independent accuracy over a long extended period of time. You need to be user-independent. And that basically meant we needed to think about probing techniques which are autonomous. And that's where our group started to think about machine learning algorithms and artificial intelligence. Now, probing techniques. So there is aligning the probe with respect to the substrate. There are a wide range of alignments that are necessary. So you need to contact the device, but before contacting the device, the probe and the substrate needs to be planar, meaning all three tips should touch the device, not only as one tip. And then after touching the device in the test, you need to also control the over travel distance, meaning to ensure a good electrical contact, we push the probe a bit more into the device. Now that's normally called an over travel distance. How long should that be? And then of course your horizontal alignment, with respect to which point do you need to perform these measurements. Now here we develop a wide range of techniques. For example, we use the RF sensing principle to contact the device automatically. So by moving the probe in height, during this movement we acquire the reflection coefficient measurement of from the DNA, and that basically is a way of assessing the height. And then the nice thing is we found a method in which we could detect this point of contact using the data simultaneously during the contacting. And by doing this, we were able to develop this optimized contacting technique, which basically has resulted in a much more improved repeatability than manual coding there. Another very important aspect is improving is alignment. So meaning if you need to contact this device and you need to contact a certain position, with respect to a certain position, how to align this probe with respect to your device. So for this, why is this important? Here you can see even 5 micron error in the alignment results in actually much higher error in the VNA measurements than we can claim. So there is a strong need to do this, and these are very low frequencies. We haven't even gone above 100 GHz yet. Now for this we needed to develop so-called object tracking. So you have a probe which we call an object. You need to be able to detect and track that object within a certain accuracy. So if you have a system which can move with about 30 nanometer accuracy, you need a vision system that can support that kind of a resolution. And optical microscopes going down to 30 nanometer is extremely hard challenge. We don't have a scanning electron microscope or something like that on top of it. An optical microscope, it has its limitations, and staying around half a micrometer is kind of the accuracy that you can expect. Now here is a clear sign that the weakest link in your system determines your accuracy. So if your microscope is simply not good enough for that kind of resolution, you will have a very high state-of-the-art probing system, but you won't be able to use that accuracy if the camera doesn't support it. So this is a paper that we just published a few months ago. Now another very interesting way of actually tracking your probe is by using also the VNA measurements. So we found out that you can detect the edges on the substrate pretty accurately using this RF sensing. So combining data, you have a vision system, for example, for scanning your position, but apart from that, you also include coming from the VNA itself. And then this is actually a place where you want to be, because you have information coming in from independent sources, and using machine learning algorithms, you can actually make even better decisions. Now that's a domain in itself, to be honest. Planarity, for example, you want to be able to ensure a good electrical contact like here for all 3 tips. This is a bad connection because here one of the tips is not touching the substrate. Now how do we ensure that? We use basically an image processing algorithm where we actually detect the intensity of skating mount. So each of these pins leaves a certain marking on the substrate. That's why these measures are called descriptive measurements, because every connection that we make changes the behavior of the device. And so we make a contact, a series of contacts, and during which we change the planarity, so the angle of the probe. And using this algorithm, we were actually quite successful in planarizing the probe within a certain region. And this is actually done, and for a naked eye, seeing this is already pretty challenging, and planarizing the probe by manually is actually much less accurate. So this was quite an interesting thing. Another very interesting parameter that we could estimate using the vision system was the overskating distance. So there's pin markings which are left on the substrate, and we performed a series of contacts, and in these contacts we changed the overskating distance. And here you can see the estimated data, which are the markers, are following this trend pretty accurately, one-to-one with the set parameter. So at the end of this, all these methods, the nice thing is that we were successful in making these on-wafer measurements user independent. Every probing alignment technique that needs to be performed prior to the measurements, we were able to optimize. And the funny thing is, nowadays form factor, which basically sells Cascade, which sells these probing stations, they have their own software as well, which claims similar performance as us. Now, probing station, probing methods, the next thing is reference standards. You need reference devices to calibrate your on-wafer system.
Excuse me, can I ask one question? At this point, sorry for the interjection. So, up till now, it's all measurements are being done by S parameter measurements.
Yes.
So, RF sensing also means S parameter measurements.
Yes, because indeed. Development of these reference standards is a domain in itself. You can buy commercial reference substrates like these from Cosset Microtech, which have a range of devices on them. However, the problem is these are not traceable. We don't have reference data given by the manufacturer, and which basically means that for any traceable measurement that we want to do, we need to design our own reference standards. And for this, we had a European project which finished a couple of months ago. And in this project, we developed our own reference substrate, which included a range of devices which were designed for calibration purposes, but also for accuracy verification purposes. We had this ability to design our own structure and reference substrate, so we designed a range of additional devices such as attenuators, mismatch lines, which could give us more information concerning the accuracy of the measurement. Now, the first thing that we do for traceability is we independently measure the properties of these structures. For example, the tolerances on all of these dimensions. Once we know these, and once we know how accurate these tolerances are, we can propagate these, and here you can see a nice overview of this actual substrate that we designed. And what we do is we propagate those tolerances through these EM simulations, and as a result, what we get is a variation on the S parameter. Okay? So here you can see a certain nominal value, and then you see a certain offset, maximum minimum offset from that nominal value, and we can say something about the accuracy of that standard. That's basically what we need from the reference device. So this, and here you see a part of the result. This is the first comparison in the world which actually went up to 1.1 terahertz. There's a paper which is now currently in the review, and which we did a comparison within the European Union, I think about 8 or 9 NMIs, and we collected data from about 10 gigahertz up to 1.1 terahertz, and we were able to estimate the accuracy also of such standards. Now, I've been talking about connectorized and on-wafer measurement, collecting all of these uncertainty estimates of each and every element involved in this measurement setup, but how to propagate these errors and compute an accuracy of a device under test. So one parameter with one accuracy uncertainty estimation on top. And for that, we basically designed our own measurement software, which is able to acquire the data from the instrument itself. So we collect the data, we don't use the firmware on the instruments, right? So which is provided. We do all the processing on the computers ourselves. And we have a software which is basically responsible for data acquisition. Then we have a module which basically calibrates this data, so de-embeds the error and calculates uncertainty. And then visualizing this data, we have a very nice module that visualizes the data. You saw the earlier graph. And then, of course, a database in which we store all the accuracies and uncertainties of every element that's involved. And then, of course, we generate a report about the measurement. Now, how to propagate errors? Now, in order to actually propagate errors of individual components, you need to develop a measurement model of the system, an equivalent model. So if you have a two-port system, you need to come up with a two-port model. And here you can see a flow graph of a two-port on-wafer measurement. These are the DUTS parameters that you need to estimate, and the uncertainties, corresponding uncertainties. You have a VNA, you have error terms, extenders, probes. Each of these need individual characterization. Once you know these values, you can use this the covariance-based uncertainty propagation method that we use to propagate these uncertainties. This is all linear measurements. At this point in time, I haven't talked about the non-linear measurement. That's a domain in itself. And then basically you come to this conclusion that you have a nominal value with a an uncertainty estimate on top of it. Now, I will be now talking very briefly about some other applications that we serve. For example, these new type of materials which are being used to design these devices, which offer very different impedances that we are actually currently used to. Now, how to actually tackle that problem? Why is that a problem itself? If you look at the noise behavior, and this is all about RF sensing, in these applications we are not that much interested in the absolute value, but relative measurements. So with respect to one certain measurement, we want to detect extremely small differences. Now, that's where the instrument resolution comes into place. So we talked about noise. Now, noise behavior of VNA for matched devices is much better than for mismatched devices, which you can see here. Now, there are many reasons for that, but I won't go into details. But the problem is that if you look at the accuracy of a measurement or impedance measurements at 50 ohm, it's actually extremely accurate, as you can see here. But when you start going into mismatched loading conditions, which are actually here and here, you have a very inaccurate measurement. So the resolution basically suffers. Now, for this application, what we did is we developed the so-called, we use the so-called interferometric principle. Basically what that means is we fool the VNA by making it think that it's actually measuring a 50 ohm device while it's measuring a very highly mismatched device. And how do we do that? Now, matched device means that your scattered wave is extremely small. Right? So if you have matched 50 ohm load terminating the VNA, you have a very small reflected scattered wave. But in a mismatched loading condition, this scattered wave becomes very big. So what we do is we develop this interferometer which copies this incident wave and then basically cancels out this scattered wave, which is reflected by the DUT itself. We generate a second wave which cancels this one out. And the resulting B wave, which goes into the instrument, is extremely small. So the VNA thinks it's measuring a 50 ohm device while measuring this highly mismatched loads. Now here you see a setup, the first prototype setup that we designed, and using off-the-shelf components, of course. And here we have digital to analog converters which control this IQ mixer, which is used for vector modulation. And so generating this second wave that we introduce into the machine. Here you see a second prototype, which is a module, so much more compact. And this module was designed for operation from, I think, 2 gigahertz up to 18 gigahertz. This is still, I think, till now the only broadband measurement that has been published for extreme impedance devices. All the other literature is single frequency based. So here we were able to show that the noise behavior under conventional VNA, which are the gray bars, we can actually reduce the error now by using this interferometer, which is, I think, the black data here, for these two impedances. So I think 500 ohm and 5 kilo ohm impedances, and we were able to reduce the noise error substantially. Another application for using this interferometers is scanning microwave microscopes. In the physical domain, there are a number of applications where they need to be able to sense very small differences of surfaces for material investigation purposes. Now, scanning microwave microscopes basically scan certain object, and because these objects are very highly mismatched, they suffer from the noise of the instrument. So we use this VNA interferometer to cancel the scattered wave, make the VNA think as if it is measuring a very small 50 ohm device, while we are actually scanning this highly mismatched surface. And we were able to demonstrate a significant improvement in resolution for such a measurement as well. Another very interesting paper that we produced was on the calibration side. So, of course, we want to look at relative measurements, but there were applications where absolute accuracy was also needed. And unfortunately, because all the other literature only focuses on single frequency measurements, they weren't able to show one of the problems that these interferometers suffered from, and that was the nonlinearity. These interferometers are actually sensitive to whatever you connect to the port, meaning you need to rethink the calibration methods that were being used. And because no one published broadband data, they didn't produce an error in those measurements. So in this paper, we tried to actually solve that by measuring this injected base separately, and we were quite successful in doing that. And you can see it here. So the next one of the projects that I would like to offer positions for students is to look towards two-port interferometer measurements. And that's something that we are quite interested in the near future. Finally, some words for nanoscale devices. So basically, in these applications, physicists from Delft, they needed to have a measurement capability to characterize these carbon nanotubes, which are actually offering a great potential for a range of applications. So here we designed a dedicated substrate because at this point of time, there are no probes going down to nanometer dimensions. So we needed to use conventional probes, meaning that these carbon nanotubes needed to be embedded in access structures which were much bigger in size. So you can see here big access structures, and in between those access structures, we basically embed the carbon nanotube, very small, as you can see here. Now, the structure is itself in the range of a couple of hundred micrometers, while the carbon nanotubes is actually in the order of tens of nanometers length and a couple of nanometers width. So we embedded these nanotubes, as you can see here. It took quite a lot of challenge. It was quite a challenge to actually make them stick on these substrates. So we needed to come up with some new type of techniques to do that. But surprising even to us, we produced some good results for these measurements because I wasn't very optimistic of these results because of the access structures. They were simply too big. But we were able to demonstrate clear sensitivity to the length of the nanotube which was being measured, and in the different access structures, and which you can see here. So that was an interesting result for us as well. Now, finally, some words on the cryogenics. So another new project that's about to start in the coming month is basically for the content group at QTech in Delft. Because of these quantum computing applications, they rely on RF sensing. Now, previously, it was all fine because they were only producing a few number of bits for these quantum computer applications. But now, in the upcoming years, they're actually substantially increasing this number of bits. Meaning, whereas previously the RF sensing without any calibration, without any accuracy estimation was still good for their application, they need to now produce better results because the differences that we now need to look at are much smaller. The increased number of bits requires a better accuracy on RF sensing. So this project will be extending S-parameter measurements in cryogenic conditions, which is a challenge because cryogenic condition means near 0 Kelvin, which means you need to think about the probes, cables, reference standards, which don't exist at this point of time. So we need to develop all of those before we can even start saying something about accuracy in cryogenic environment. Finally, my closing slide, which I think feels is actually something which holds very well in our group. We start with a measurement system. We claim we can measure very accurately, but after years of investigations, we start thinking about, okay, the accuracy needs to be reduced because we have lesser confidence in the measurement. And that's something that's quite true for these applications. So finally, I would like to close my talk. Thank you.
Questions, please. Go ahead.
Excuse me, sir, can you explain in some detail about cryogenic temperature?
Yes. Well, cryogenic means at 0 Kelvin, near 0 Kelvin, minus 273 degrees, I think. And I'm by no means an expert on quantum computing. The only thing that I know is they need accurate RF sensing capability. That's where my domain starts. So RF sensing means you need to detect very, very small differences. And doing that in the cryogenic conditions means that you need to develop a probe that can handle that temperature. You can buy something commercially, but not very necessarily accurate probe. Cables, because the cable is actually at one end, it's at 0 Kelvin, at the other end, it's in the environment, conventional environment. So you have a very big temperature gradient, right, going through. How does the cable handle that? And then the biggest question is, how do you even calibrate in that condition? You can't go yourself and connect a device, a reference device. So you need to be able to change reference devices in cryogenic. You need switches, which also don't exist, at least with the accuracy that we need them for. So the challenges are that for metrology applications, there's not much out there. And you need to develop each and every element. And that makes it also very, metrology is something for people who are able to handle long projects, because it won't happen in a year. We need a substantial amount of time to tackle each of these components one by one.
Right. Any other question? Atta?
So, what are the fundamental limit on size of the probe, RF probes?
Yeah.
Meaning, when does the quantum effect of the probe come?
A very good question. We have now a project which is ongoing, in which we aim to develop a probe with pitch sizes of 1 micrometer. Currently, you can buy the smallest pitch size you can buy is about 25 micrometers. Unfortunately, we ran into manufacturing difficulties. The ideas that we had and the techniques that we wanted to try to design those probes didn't work. And that's what R&D is all about. You need to try new things and see how it works out. Unfortunately, in this case, it didn't work out, and we are now looking into other methods. And the issue there is we are limited by the manufacturing capability. So we tried glass materials and some other techniques as well to move the tips extremely close to each other. Another probe that you saw in this slide was MEMS wave probes. Those were quite successful, but the problem there was that we were limited in the frequency. We were only able to go up to about 20 gigahertz, and if we want to go to much higher frequencies, we needed more work and more funding.
It would be even a bigger problem.
Yeah, as you all know, the RF domain is an extremely costly domain to work in, so we need to rely on funds, and especially doing things like these. We need to develop first reference devices, as MEMS structures we need to develop exhaustively, tested before, and then you produce them, and you need to have patience.
Yeah, saw your hand go up.
I have two questions. Very, very nice talk. Really enjoyed it. First question is, when you do broadband measurements, truly say hundreds of gigahertz, do you get waveguides or cables that can handle this big range?
Yeah, precisely. We rely on, actually, let me show you one of the slides, and it was just one graph, I think. Yeah, this one. I think it took about 2 or 3 weeks of measurements to make this one graph. And what you are asking for, indeed, for this broadband frequency range, we covered about 6 frequency bands, waveguide bands, which means every time you need to disassemble the system, put up on a different frequency extender unit, because we need to switch from one frequency band to another, and repeat the entire calibration measurement process 8 times almost. And that's why it took us about 2 to 3 weeks to make this one graph. Actually, it's redoing the same measurement, but then for the different frequency band. At this point of time, there's no frequency extender unit that can go from 10 gigahertz to 1.1 terahertz. You need to buy these waveguide bands. One frequency extender goes from 110 to 220, then you go from 220 to 330, 330 to 500, 500 to 750, and 750 to 1.1 terahertz. So it's a lot of repetition.
That's physical limitations anyway.
Yeah, yeah.
You won't be able to. It's not good. The structure is not going to sustain.
Yeah, that's also another challenge.
So
The structure, because it's destructive measurement, so we needed to manufacture enough structures to allow us to do this. So we were able to manufacture this reference substrate, and we made about, I think, about 50 structures, and we made a lot of replicas, because we need to measure the same structure many times. And because once you measure them in one frequency band, when you switch to the frequency band, The one that you measured is already destroyed away. So you measure fresh new one. So it's an exhausting process, to be honest. A lot of patience.
And at these very high frequencies, I think these probe tips, they would also start acting like antennas.
Yeah, yeah. They
So
actually.
how do you, because that's, this EMI problem
Yeah.
might be very severe, so how do you address that?
Yeah, that was a slide sooner, but we do indeed, what we did is we made equivalent models of these probes, and at high frequencies, indeed, they actually start acting, radiating like antennas from about 10 gigahertz onwards already. The thing is that up to about 100 gigahertz, still this crosstalk is still relatively low. It's not dominant. But when you start going from 100 gigahertz to higher frequencies, it's actually one of the most dominant effects. That's why we need to assess it within a certain range before we can even claim accuracy. And there are a number of techniques to de-embed and tackle that. The 16-term calibration method, for example, we need to design dedicated structures for crosstalk estimation. But that's a domain in itself.
My last question is, instead of doing optical tracking for probe approach in an automation process, will it be possible to actually use some tunneling microscopy techniques to look at approach and do it in a controlled fashion? Because I think they do employ control algorithms, but more advanced algorithms as well, which are machine learning based.
True. That's also one of the things that we tried. I didn't show that here, but indeed we use independent lasers and PSD detectors to track the height of the probe. And you can do that for same for the horizontal lining. The challenge there is that it will make the system even more complex. And you're adding another source of information. Of course, it allows you to track the probes with a certain accuracy. Now, I think a very good question, because I think that will be the solution, because the optical microscopes are at this point limiting us. We are not able to move the probe with the accuracy as the probing station can, because of the optical microscope. It has about limited limitations up to about half a micrometer. And to go below that number, we need to rely on some other data.
And I saw you were using some pico motors.
Yes.
Red color ones.
Yeah.
I think one of the problems those motors may have, even though they do mention their resolution, spatial resolution is about jitter.
Yes, there are actually.
Uniform.
Yeah, that also very good question. I think that's a top that we investigated these motors quite intensively, to be honest. And indeed, what you say here, there are a number of errors that actually are produced by these motors. The reason why we chose them is they are low cost, and they're relatively low cost with respect to the high precision transformation stages. And in the third prototype, we are actually replacing those. And because they indeed produce a lot of different type of errors which are very difficult to handle in a planar domain. Now, these errors are still small enough for micrometer scale measurements. So if you want to do conventional on-wafer measurements, they're good. But if you want to go towards nanoscale measurements, then this probing station will need to be revised extensively.
Just one last thing. One suggestion or maybe idea is, if you want to reduce the complexity, you don't want to add more gadgets for automation or anything, maybe the best approach would be laser interferometry, in which everything remains remote. You just shine a pulsed laser, perhaps a femtosecond or a femtosecond laser, and look at interferometry to detect motion and where your objects are.
We did investigate, and we actually hired an external consultant to advise on how to redevelop and redesign the system to achieve kind of 10 nanometer kind of a resolution. The problem was the cost. It really exponentially increased the cost on the system side. So the thing is, at this point of time, nanoscale probing is more R&D based, and we start thinking about these developments when it has commercial value. So at this point, because there are only very limited number of people who are interested in these measurements, and all of them are coming from the academia, and our development starts when basically a commercial value starts, a commercial companies start asking for these measurements. So that's what we did. We did investigate other possibilities, but we were actually, those were put on hold at the moment simply because it's too complex, too costly.
Do we have a question from someone else?
Thank you.
Any other question or comment from you, sir? All right, thank you very much.
Pleasure.
Lovely talk.